Hello, teachers and classmates. Today, our team will present the report Finding the Value Formulates of Spheres, a historical and mathematical explorations. Our team members are 何万佳、廖凯华、陈丹、林瑜、左鹏、何一凡、何小娟、张思琪 and 郭子涵. Next, I will introduce the basic information of these lessons. This lesson is for 10th grade students. They have a basic understanding of 3D geometry, can calculate the value of presents and primaries. These lessons last 45 minutes. One class points. They should already know how to find the area of a circle, the value of cylinders and a cone, and the Pythagorean theorems. We have prepared videos, shape models, and practice papers to help teach. There are 4 main learning goals. Learn about the history of formulas, learn how to use Jugen's principle to prove it, get a simple idea of calculus slicing, and build basic math skills. Next, we will talk about our teaching ideas, math history, how to get the formulas, and more. That's all for the basic information of the course. Let's welcome the next presenter.
Today, we will present our math lesson design besides on HPM, history and pedagogy of mathematics. Let's start with our outline. Teaching philosopher and overall design. Ancient Chinese and Western math history. Formula derivation, Jugen's principle and modern calculus. Classroom activities, practice, worksheets, and our conclusion. Our core is HPM. We integrate math history into teaching to spark students' interests and deepen our understanding of math essays. Our teaching flow has 5 steps. First one, scenario introduction with a real-life example. Second, history review of ancient contributions. Third, formula derivation of Jugen's principle. Fourth, practice and fun application activities. The last one is summary of key takeaways. In class, we use 3 activities types. Group discussions for collaborative thinking. Hands-on experiments like water displacement. Historical inquiry to explore math origins. That's our fine work. Now, let's begin with history of mathematics.
Following the previous sharing, I will now take you through the ancient Chinese contributions to the study of sphere volume. First, we look at the 9 chapters on the mathematical art, an ancient Chinese classic. It recorded an approximate formula for sphere volume. Though not precise, it showed earlier Chinese mathematicians' first attempts to measure curved solids. Next, Liu Hui, a great mathematician, found flaws in this formula. He created a geometric model called 谋合方盖 and proved the volume ratio of the sphere to this model is pi4. This was a critical step toward the exact formula. Building on Liu Hui's work, Zu Chongzhi and his son Zu Geng completed the solution with Zu Geng's principle. If 2 solids lie between parallel planes and their cross-sectional areas are equal for any parallel plane, their volumes are equal. Using this principle, they derived the precise sphere volume formula. This shows the continuous wisdom of ancient Chinese mathematicians. Now, let's hand over to the next speaker.
Next, I will introduce how the ancient Greek mathematician Archimedes calculated the volume of the sphere. Archimedes didn't attempt a direct calculation, as this would have been extremely difficult with the mathematical knowledge of his era. Instead, he used a very clever and in general method involving physics and lever. Actually, he called it his mechanical method. So here what he did, he imagined a sphere, a cone, and a cylinder. The cylinder was special because the sphere fit perfectly inside it. So we call it a circumscribed cylinder. The cone had the same base and height as the cylinder. Archimedes then used the principle of the lever, like a seesaw. He placed the sphere and the cone on one side of the lever, and the cylinder on the other side. Through reasoning, he showed that for the lever to balance, the combined volume of the sphere and the cone must be equal to the volume of the cylinder. In this way, he deduced the relationship between their volumes. Basically, he proved that the volume of a sphere is exactly 2/3 the volume of its circumscribed cylinder.
Next, let me to introduce the formula derivation of Zhugen's principle. First, the core content of Zhugen's principle is that if two geometric solids are sandwiched between two parallel planes, and any plane parallel to these two planes intersects them, producing cross-sectional areas that are all equal, then the volumes of these two geometric solids are equal. And now, let's watch a video to watch the animation demonstration to get more about this principle.
I'll present the derivation of the sphere value formula using modern calculus, the slicing method, and compare it with ancient mathematical approaches. First, let's look at the geometric setup. We treat a sphere as an infinite stack of thin circular disks, just like stacking pancakes. We place the sphere in a coordinate system centered at the origin, defined by this equation here. At any position along the axis, the radius of a slice is given by this expression, derived from the Pythagorean zero. The tiny value of one thin slice is then the area of the circle times its thickness, which simplifies to this form. To find the total value, we sum all these tiny slices from negative r to r using a definite integral, as shown here. We first find the antiderivative, then apply the fundamental theorem of calculus to evaluate the limits. After simplification, we arrive at the well-known result. The value of a sphere is 4/3 pi r cubed. Finally, let's compare ancient and modern methods. Ancient mathematicians like Archimedes used the method of exhaustion, relying on geometric bonds and proof by contradiction. Meanwhile, Huygens' principle used visual geometric equivalence. Our modern slicing method, built on limits and infinitesimals, turns these older geometric intuitions into a rigorous algebraic framework. In short, calculus systematizes and elevates the insights of our predecessors.
Okay, I'll quickly introduce our classroom activities and fun cases designed to make math learning lively and practical. First, historical discussion. We'll explore the genius of Archimedes' proof method, how he calculated sphere value over 2,000 years ago, and compare Eastern and Western mathematical traditions. This helps us see math as a living, global story, not just formula. Next, fun activities design. We do 2 hands-on experiments. Point stacking will visually show the slicing method for hemispheres, and water displacement will help us verify the sphere volume formula with a cylinder, turning abstract equation into tangible results. Then, fun example. We apply our knowledge to the real world, calculating Earth's volume using its average radius, and measuring a real basketball to find its volume and surface area. This connects classroom math to the things that we see every day. Finally, our learning outcomes through discussion, hands-on experiment, and real-world application will deepen in understanding, master core concepts, and see math as a useful tool to interpret the world. Thank you. Let's move on to the next.
To consolidate learning effects, we have also designed differentiated practices and worksheets. Basic calculation problems help everyone proficiently master the method of finding the sphere's volume, given radius or diameter, laying a solid foundation. Historical inquiry problems ask everyone to describe the main steps of Huygens' principle or Archimedes' proof, deepening the understanding of the derivation process. There are also differentiated tasks. The basic task is to complete required exercises. The advanced task is to attempt to derive the formula independently. And the practical task is to measure spherical objects such as table tennis balls and basketballs at home and calculate the volumes. Evaluation will comprehensively consider calculation accuracy, completeness of the derivation process, depth of historical understanding, and the quality of practical reports, making the evaluation more holistic.
Now, let's sum up our lessons for conclusion and reference. First, for the key conclusion, for the sphere volume formula, we have 3 ways to work it out. 2 are ancient Greek methods, Dugan principle from China, and Archimedes method from Greece. The modern way is calculus slicing, and it comes from the old mathematical ideas. Then, let's compare our teaching designs with the traditional one. Traditional teaching just tells students the formula and lets them to do exercise. It has no mathematical history, only letting students know how to calculate for exams. But our teaching combines math history with teaching. We guide students to find the formula step by step and compare Chinese and Western math wisdom. It helps students understand why the formula is correct, feel how math develops, and train their local thinking. Finally, we have 3 straps. We mix Chinese and Western math history, link old methods to modern calculus, and use stories to make math easier. We also have limits. History takes more time. Some students struggle with old new connections and we lack level text. For improvements, we will use handouts, short videos, and layered text to make teaching better. For the reference, you can see all the context of our lesson is based on the reference on the screen. Thank you for your listening.